We are going to use the rate equation for first order reactions to solve this problem. Here we have the decomposition of sulfuric chloride given by this reaction. We know that it follows first order, the decomposition follows first order kinetics. Experiment was done and the concentration was monitored at a given temperature over a period of time, and 2 data points were collected. We're going to use these data to solve for K. So we have 2 times, 200 seconds and 300 seconds, and we have the concentrations at each of those times. So this time right here, that will be at 300 seconds. We'll say that the original time is 200, the time is 200 seconds, so we can solve for K. So natural log of the concentration at time t, that's 0.0917, equals the natural log at the initial, for us that's going to be 200 seconds, minus K we don't know, and time, the difference in the time is 100 seconds. So now we can solve for K. Go ahead and solve for K. You get K equals 2.9 0, we have 3 significant figures, times 10 to the minus 4. It's first order, so who knows what the units of K are. Reciprocal seconds. Done with this problem. I'm just going to take a couple of minutes to do a few things here. If you understand, you're good to go. If you're wondering how I knew that the units for K were reciprocal seconds, remember rate equals K, and if this is first order like that, units, so rate equals K. Units of rate would be molarity per second. K we don't know, and concentration is given in molarity. So if we're solving for K, we're dividing both sides by molarity, leaving us with 1 over seconds, which is a little awkward. We write reciprocal seconds. So that's how we get the K. And if you're wondering what I did in my calculator, let me show that. I'm going to start with the second part so that I can use fewer parentheses. So I'm going to key in natural log of 0.0944. Press enter to get the answer. And now I'll key in natural log 0.0917. And then I will subtract second answer. I want to subtract this value. I'm not sure if I need parentheses there. Whoops. So how about I'm going to delete. How can I go back? Here we go. Enter the parentheses. And now subtract second answer. So I've moved this to the other side. So this number here that I'm showing in the calculator equals negative K 100. So I want to divide by both sides by negative 100. Divide by negative 100. And that gives me the answer. That's how I got the answer. Some of you may be wondering how we derive the rate equation. So if you're interested in that, how I derive the integrated rate law, I'll show you how I do that. This will not be on an exam, but some of you are taking calculus, have taken calculus, and are interested. Some of you may be wondering how I derive the integrated rate law, and I will show that now. This will not be on an exam, but for those of you who are currently taking calculus, have taken calculus, you might be interested in this. The first thing I'm going to do is write the rate expression, and if you'll permit me, instead of writing the rate expression for the sulfuryl chloride, I'm just going to consider that the reactant is A. I've written the rate expression in terms of the reactant, and I've written the rate law for a first order reaction. Now you can see that rate must equal rate, so I'm going to substitute and say that this component equals this component. The negative change, negative because A is being consumed, negative change in concentration of A with respect to time equals K times the concentration of A. So let's integrate now. Pulled out the negative here and change, I just call it dA dt right here. So we're integrating both sides of the equation, and why don't we multiply both sides of the equation by dt, and at the same time divide by concentration of A. So actually let's multiply by negative, both sides by negative dt, and divide by A. Multiplied both sides by negative dt, as you can see, divided both sides by concentration of A, and let's pull out the K, this K, pull it out. So I'll have this right here. Now we're gonna, the integral, of course, is the natural log. So we've got natural log A of t subtract natural log A initial equals negative kt. So right here you have the first order integrated rate law, and sometimes just so we don't, so a lot of people then add this to the other side. That would give us natural log A of t. Just added the natural log of A initial to the other side. Whoops. I have a little typo here, don't I? There's no equal sign here. There we go. Some people like to write, I like to write this as natural log of concentration of A at some time t equals negative kt plus natural log of the concentration, the initial concentration of A. And the reason I like to do this is because this gives me the sense of equation of a straight line, and I'm sure that you've read that we can actually graph these data, and you've got natural log of A at some time t, and this is your y-intercept right here. That's this portion right there. And your slope is negative k. And this is time on the y-axis. So in this problem that we did, we only examined 2 data points, but of course the data would be, the k would be more accurate if we had many data points. And so in the laboratory, we actually collect many data points and get the k and solve for some concentration at some future time. And that's all in this video.